All right, so obviously ONOS config is the thing that we're all starting to work on a lot more, and it's an old project. Like we started what, like a year and a half or two and a half years ago? Two and a half years ago, yeah. So it has an old code base, and we've learned a lot. That was like our first Go project, so we've learned a lot since then. Just to sort of get us like bootstrapped, we need to go over. I'm going to go over parts of the internals that I'm responsible for, and then some of the changes that me and Adib are talking about making. And this is probably the stuff that I'm going to talk about is probably the part of ONOS config that is least well understood by other people, which is why I think it's important to cover. So I'll do that in this meeting, and then Sean will cover the other parts that I don't cover in here on Friday. Yeah, so this is sort of like half of a presentation. I'm going to go over a little bit of the concepts that are relevant to what I'm going to talk about, and the structure of the project and things like that. And then the big thing that I want to talk about is the controllers, and then, like I said, what me and Adib are proposing to change. So obviously, ONOS topo, which we've talked about before, is relevant to ONOS config. So config uses the topology to basically discover, currently they're called devices, in the future they'll probably be called targets, but basically it just watches the topology for entities that it's interested in being created, and those entities, the aspects in those entities tell it how to connect to some GNMI target on the southbound. And then, so yeah, GNMI, ONOS config, both on the northbound and southbound, has a GNMI interface. So the northbound, it's a server, so it basically looks like any other GNMI target. And then on the southbound, it has a GNMI client that uses to talk to GNMI servers on the southbound. And then ONOS config sort of acts as the source of truth for the configuration of those devices on the southbound. So changes come in through the northbound. It has an internal state, and that's considered the source of truth for the targets that are on its southbound. And so its goal is just to make those targets configuration match the source of truth inside of it. And then there are model plugins, which I'm not gonna talk about. The way that ONOS config learns about the Yang models relevant to targets is with a plugin system. Currently, that plugin system is implemented with Go plugins, which are terrible and have been a huge pain in the ass. And so Thomas is working on moving to a different architecture, which we can talk about if we have time. I don't know if we'll have time though. Yeah, and then so relevant to this talk are a few concepts. So transactions. So one of the things that ONOS config provides is basically support for transactional changes, transactional GNMI sets. So you can do a GNMI set on the northbound that actually configures multiple targets, and it will it treats them as a transaction, so it will apply all of them as one to multiple targets, and basically it serializes transactions. So transaction to multiple targets will be applied on the southbound before any later transaction is. And I'll talk about how that's done, which is what's important. And then the state that's stored inside of ONOS config, there are lots of stores. I'll go through the code pretty soon. All the stores, or a lot of the stores, are backed by atomics primitives. There are a couple of primitives like the transaction log. We made a new primitive for that, which is it's called indexed map. It's like a map that you can, it's like a sorted map basically that has indexed entries, which we can use to randomly update entries in a log or append entries to a log. And this is what provides the order. This is what determines basically the total order of changes that are coming into ONOS config and the order in which it will apply them to targets on the southbound. And then with any log, the problem is that it eventually grow infinitely, and it can't grow infinitely. And so it has a snapshot mechanism, which basically when changes, there's like a couple settings that, if I recall correctly, if it can roll up the changes that are of a certain, like past a certain age, or when the log is beyond a certain size, it will roll them up into a snapshot, which is basically just like an aggregate of all the changes that it wants to remove from the transaction log, and then it stores that in just an atomics map. And then that allows it to delete changes.
Does it squash all the changes together or just move them somewhere else?
Well, that's what the snapshot is. So it basically squashes, yes.
Okay.
It basically goes from the earliest to the latest, and basically computes all the path value pairs of them, and then stores that in a snapshot, and then it can delete those entries from the log.
Okay.
So the project structure. So so there are some extra. Obviously, it doesn't define GNMI. GNMI is its own thing, but we do have other services that it defines. Let me find them in ONOS API. Yeah, so in ONOS API, there is a config package which defines some administrative APIs, changes, which I'll talk about in a second, which these are how basically it tracks the operations that those basically represent the state changes that are being requested. There's a diags API and then the snapshot. So this is where all of the things that I'm going to talk about are defined later. ONOS config follows the standard Go project layout. So there's this Golang standards org on GitHub that basically describes like a recommended project layout. That's what all of our components follow this. But mostly the relevant packages that you'd be working in are package and test. So if you go look at ONOS config, yeah, there's build scripts in the build directory, Go commands in the command directory, and then package is where all the good code is, and then test is the helmet tests. And then, yeah, inside of package, basically, so manager is basically what we call the manager, which is, it basically starts all the other components. So when the ONOS config command is run, which is run by the Docker container, it calls this manager, it tells it to run, and the manager will create all the stores, create the controllers, which I'll talk about, create the northbound server, and things like that. Start listening to Topo or whatever. The northbound has the northbound servers. Southbound has all the management of the GNMI connections on the southbound. Stores is where all the atomics stores are. And that's, oh yeah, and then controllers, which is what I'm going to talk about. Or basically, that's basically where all the logic for basically propagating changes on the southbound lives. So that brings me to the controllers. So the controllers, this is a common pattern that we use throughout a lot of our services now, and it's inspired by Kubernetes. So Kubernetes is a control plane, and basically the way Kubernetes works is you give it something that you want to deploy. You say, I want to deploy a stateful set or a deployment or whatever, and it continuously works to make that happen. That's why when it's like a self-healing architecture. So if you give it a deployment and it you say create 3 replicas, it creates 3 pods. This is why if you go and delete a pod, it will just recreate it, and this is the pattern that gives Kubernetes that sort of property of the self-healing property, and it's great. It's something I wanted to do after, like in classic ONOS, especially in production with Comcast, we found just relying on events basically made the system really fragile, because you're really highly dependent on the reliability of event delivery and things like that, the order in which events are being delivered. And this basically is much more robust because it doesn't care about order. It doesn't care, like if things are lost, it can tolerate that easily. And so the difference is that it uses this, what they call level triggered, this level triggering paradigm. And the idea is that, yeah, like it said, rather than reacting to events, or rather than reacting to a request, you're basically just like I said about Kubernetes, you tell Kubernetes what you want to deploy and it tries to deploy that. And so the logic in ONOS config is interested in what you want to do, not some event that you requested for it to do. You'll see, I have some examples of what it means. But this is
it's opposed to edge triggered, right? You have edge triggered and level
yes,
triggered, right?
exactly. Yeah, this is an interesting thing to read if you want to understand it better. Yeah, and so basically the level trigger design, basically the logic in ONOS config cares about the state of the system rather than events that are happening in the system. So it doesn't care that you requested a change. It basically cares about what the configuration of the target is supposed to be and what the configuration of the target currently is. And that makes it more resilient to failures on the southbound. And so it's like declarative. So like the Kubernetes API is declarative. You declare what you want rather than tell it create a pod, create 3 pods or whatever, create a service. And so yeah, you basically in the level trigger design, you declare the desired state, and then ONOS config continuously reconciles that desired state, which is the configuration of a target, with what the actual state is, which is if you were to do a GMI get, what is the actual configuration of the target versus what we want the configuration of the target to be, and then it reconciles those two. And so we actually have, and this is the paradigm that you're implementing when you build Kubernetes operators, which are just controllers. And we actually have, so in ONOS.Lib Go, we have our own version of the same framework. So inside of Kubernetes, they have their own controller framework, and it looks very much like this because this is very much based on what's actually inside of Kubernetes. And the important interface here is this reconciler interface, which I'll talk about. And so basically, the way the controller works is it has like a set of watchers, which basically just listen for state changes in the system, and then a reconciler. And so some set of watchers, which I'll provide some examples, but some set of watchers are saying, hey, let me know when the desired configuration changes, or when a device appears, or when a device goes down or whatever, and then trigger reconciliation when that happens. And reconciliation is where all the logic lives. And so when some state change happens in the system, this reconcile method is called, and it's saying reconcile some object. So reconcile this target or whatever, and then the reconciler will say, okay, so what's the desired state of the target and what's the actual state of the target, and it will figure out the changes that it needs to make to get from the actual state to the desired state. So that's how controllers work. And this is actually, this sort of paradigm is really easy to specify in model checking, which we've also done and are also using. What was I gonna do? So let me get to the examples to make this more concrete. Yeah, so like I said, basically when a relevant state change happens, targets added, targets connected, disconnected, store changed, or master strip changed or something. The reconciler compares the desired state to the actual state, changes the actual state to progress towards the desired state, and that is basically run in a loop over and over until the reconciler says there's nothing left to change. Which in this API, by the way, dang it, this freaking thing is in my way. Which this API, the way it works basically is, when you reconcile some object, if you just return a result, so the result, where's the result? Yeah, so the result has like options for requeuing to reconcile again later, things like that. But if you just return a result and say that has nothing in it, basically, that means there's nothing left to do, and just wait for some other state change to happen. And also the nice thing about this is that it automatically retries errors and does exponential backoff and things like that. So if some state change happens and the reconciler is called, and say on the southbound it does like a GNMI set and the set fails or whatever, the reconciler returns the error, and then the controller framework has basically a loop, which is down here, that will retry and do backoff and things like that.
So a quick question.
Yes.
From the perspective of ONOS config, actual state, you consider it to be whatever you successfully applied out the southbound and was accepted. Yes. Correct, you're not really concerned with the device accepting the changes, and then its actual, from the device's perspective, its actual state drifting due to problems with the device. I mean, say the device restarts.
Right, yeah, so that's the way it currently works. That's the way it currently works, but we actually have a proposal to change that, which I'll talk about. But I mean, it could work either way, but like currently, well, I'll talk about it in a second, but yeah, I mean, currently, basically whatever the device has acknowledged is considered its actual state. Whatever.
Okay, good. Thanks.
Reminds me a lot of XOS, Scott.
Yeah, that's kind of what. Yeah, it's like we did in XOS, and I think we got to the same point where we started thinking about, what happens when the state drifts. How would XOS wake up and realize that it needs to resynchronize? I think we kind of got to the same place you guys are at here with worrying about that condition.
All right. Yeah, so on to what this means in practice. So there are a few, if you look in, actually, where is it? Yeah, so this is the controller package. There are like a bunch of different controllers in here. Change controllers, which I'll talk about. Snapshot controllers, which take the snapshots. I'll talk about those, but there are a bunch of different controllers in there. I want to go over the controllers as they exist now, because we're kind of in a weird state where we're sort of in between refactoring, because we already know that we're changing some terminology and things. And so I want to try to, it would be confusing to either cover the current changes and not the future changes, or the future changes and not the current changes. So I'm going to do both. So the way that ONOS config works now, or prior to prior to us starting refactoring a couple weeks ago, is there's this, so one of the objects that is reconciled is called a network change. And so a network change basically represents a GNMI operation that's received on the northbound. So when a GNMI set is received on the northbound, basically that's immediately just appended to the network change log with just all the information that it got in that request. And so the network change contains a set of changes that are potentially to one or more devices, which I'm using devices also because that's the old terminology. It's stored in append only log in that index map data structure that I talked about earlier. And so basically that log is then, the entire log basically represents the desired state of the system. Basically, the aggregate of all the changes in the log is the desired state of the system. Yeah, and so when the change is appended to the log, it's assigned an index, which basically, that's what defines the order of changes as they should be applied. And then the way that the actual state is represented, and this is what you see in the Kubernetes API also, is in a status. So like in Kubernetes, if you look at basically any object, a pod or a deployment or whatever, they all have status objects, which these are the actual state in Kubernetes, and we followed that same pattern. And so in network changes, basically changes can be in one of two phases, change and rollback. So if you request a change, it basically first gets created in the change phase, and I'll talk about how that's processed. And then if you want to roll back a change, it gets changed into the rollback phase. And then within each phase, there are some states that the reconcilers use to determine how to process the change pending complete and failed. And then the network change controller, basically it watches for device events, which is changes to the devices in topo. So if a device state is changed to connected or disconnected, or a device is added or whatever, the reconciler will be triggered. If a network change is added to the network change store or updated, the reconciler will be triggered. And if a device change is added, which I'll talk about device changes in a second. Ooh. So if you look at, this is what the actual code looks like. If you go to the controller.go in the network change controller, at the top, basically this is where it sets up the controller. And you see that it basically is creating this watcher basically watches for changes to the network change store. The device watcher watches for changes to the device change, or to the device in topo. Device change watcher watches for changes to the device change store. And so if any of these watchers see an event from one of those sources, it will tell the controller to reconcile the relevant object.
The controller watches for changes in the stores that are within ONOS config.
Yeah.
And how are the stores updated from ONOS topo?
Oh, no. So in the case of the device watcher, it's actually watching ONOS topo. So if you look at it, let's look at the watchers.
Okay, you define the watchers as well.
Yeah, so you define the watchers. So the device watcher, yeah, the device watcher is using this device store, but device store is just calling topo.
Okay.
But yeah, you define the watchers, and these just like call, like you'll see on all of our APIs, on all of those stores, we have watch methods and things like that. And so these just call this, and they create a channel, and if some change happens, something changes a network change or whatever, it will tell the reconciler to reconcile the change again. Yeah, and then here's the reconcilers in here too. But I'll talk about the logic in that. Yeah, so those are the watchers. So when an event happens in one of those watchers, the reconciler is triggered. And then reconciliation for network changes, basically. So when a reconciler is called, it's just given an ID, not an object. And the reason for that is because you want to be, the reconciler should be operating on the current state of the system. It shouldn't care about some event. So it's not, it's not getting an event and deciding what to do with the information in that event. We're just telling the reconciler to check the current state of the system, compare it against the desired state of the system, and make some changes. So when the network change reconciler is called, it will go to the store and say get the relevant network change. If it's in the pending state, and it's a chain, it's in the change phase, it will create device changes, and then set those device change phases also to change, which I'll talk about the device changes in a second. And then if the network change is in the rollback phase, then it basically propagates that information to the device changes. And if the network change has already been reconciled, so the reconciler already set its state to complete, it will do nothing. And something that I missed to add here is it will also say it's in the change phase. It basically will check the device changes, and if the device changes are complete, then it can mark the network change complete. And that's how information gets propagated from a log for an individual device up to the basically network-wide change log. And then the network change controller is basically managing device changes. And so for each device, there's also a separate change log, which is also stored in an indexed map. So it's just a log of changes to a specific device. And it has the same basic status as the network change. Has a phase, change, and rollback and state. And then like the network change controller listens to some relevant events, device events, so that if the device it's interested in comes back online or something, it can send pending changes to it or whatever. And the logic in the device change reconciler, again, it gets the current state of the device change. If it's pending for a change, it will basically create a GNMI set and send it to that device. And if it's successful, it'll set the state to complete, and that tells the network change controller that this device has been updated, so that the network change controller can figure out when all the devices are updated and updated state. And then you'll see it like in the northbound API. We'll do things like create a network change and then watch its state and wait for it to complete and things like that. And then if it's a rollback, it basically computes the inverse of the change, the change that's in the device change object. And we'll again call it GNMI set and then set the state to complete. If the state is complete, it does nothing. Let's see. Yeah, so this is what the actual messages look like in protobuf. So network change has an index associated with it, and then there's this the status. So this is where those phases and states are tracked. And then so network change is basically just a repeated list of changes. And the device change is in here. And again, it has an index because it's part of a log, which this is what I'm gonna talk about changing in a minute. But again, it just has a status, and then it has a change, which basically is like a list of values to set, which can be turned into a GNMI set representing that device change. All right. And then there's also some snapshot controllers. So these are what basically monitor the logs, figure out when they get too long, roll them up into a snapshot. And again, the idea is just to not allow the log to grow infinitely. So the network snapshot controller watches the network change store for changes. If it's too big, computes an aggregate configuration of the changes, stores that in a snapshot, and then removes those changes so that it's not growing infinitely. So that's basically the state of ONOS config as it was originally designed or originally written. And so, but with new use cases, like when we built it, it was made specifically for the network configuration use case. And so with new use cases now, there are a lot of things that we need to change. And then also we've learned, I think, especially from building the E2T service, we've learned a lot since we wrote this. And so we have some changes to propose. So first is basically a rename of network change to transaction. So a network change basically represents changes to multiple devices. Well, I guess there are two changes here. So devices becomes targets, which basically the objects in topo that are being used to represent objects on the southbound that we're configuring become targets because they're not necessarily devices. And then network changes become transactions. And so a transaction basically just represents a GNMI set on multiple targets in this case. Yeah, and so all this stuff looks exactly the same as network change. Watches topology for target events, and then watches for changes to transactions and to the objects that it manages, which the configuration object is the bigger change. So I'm going to go over that first. So rather than, so one of the sort of, I think, sources of complexity in ONOS config was managing lots of different logs and keeping consistency between them. Basically, we have one global log and then a log for each target or each device. And it's really unnecessary because the global log, ultimately the per device logs match exactly the global log just as it relates to one specific device. And so it's really redundant and also sort of inconsistent with the level triggering paradigm. And so the idea here is to, rather than taking a transaction and then creating a per target log that just matches the transaction log, basically for each target, the transaction log gets turned into the desired configuration for the target, which this is much more consistent with the level triggering paradigm, like I mentioned. So a configuration is just like what a snapshot is in the current code base. So a list of basically paths and values that represents the complete desired configuration for a target stored in just a regular atomics map. We don't have to manage a separate log. And then so the role of the transaction controller then is to turn the transaction log into the desired configuration for each target. So when reconciling a transaction or reconciling the transaction log, when a new transaction comes, basically the desired configuration resulting from that transaction being appended to the log is updated for each target associated with the transaction. And then when it's rolled back, it's just computing the inverse.
So if I can jump in, so basically the transaction is a set of changes that come in externally to be applied to potentially multiple different targets. The controller then basically just applies that to a desired overall configuration, which can then be validated as one, right?
Which is held
Exactly.
pairwise.
Exactly, right, exactly, right. And then there will be then sort of controllers for each of the targets, which will then turn that overall configuration and reconcile using the reconciliation paradigm, turn it into sort of changes that need to be applied to the device. Got it. Okay, and it's completely separate. And but the key point is the level trigger. Got it. Okay, thank you.
Yeah. So and then for a rollback, it would basically compute the configuration for each target up to the prior transaction or whatever. Yeah, and so then the configuration controller, when a configuration is, the configuration is the desired configuration for a target. The configuration controller is responsible for, yeah, like you said, turning that configuration into whatever GNMI operations need to be performed on the target and doing that.
I really like that. It's really much cleaner.
Yeah, I think it's much less complex, and I think it actually, I think it makes mastership no longer necessary, because you can basically treat the actual target state as the actual state, rather than assuming that whatever the target has acknowledged as its actual state, you can actually ask it and compare that to the desired state. And when you do that, scenarios that mastership is needed for, like multiple masters. I mean, mastership is really important for doing things in a specific order. So making sure that, like, we have a change log, we need to make sure that like device changes is a log. We need to make sure that they're all applied in order. And if they're not all applied in order, or if some other process is also trying to apply them at the same time, you can get changes going back and forth and things like that. In this case, when we're just reconciling the entire desired configuration with the actual configuration of the target, ordered no longer matters.
Like for transaction coming in back to back, let's say in milliseconds before the reconcile start, the reconcile will actually apply the desired state as a result of the forward transaction. So it doesn't really matter which one applies, because it's always
a performance benefit in that respect too. Yeah, so the configuration controller, basically for when the configuration is updated, its state is set to pending, and the configuration controller, when it sees a pending pending configuration, it gets the state from the target, computes whatever the difference is, and then sends those set operations.
When you say gets the state from the targets, does that mean going down to the actual device?
Yeah, I think it can. We can do it. This is open-ended. I mean, I think we can do that, or we cannot do that. I have no preference.
Right.
Or we can make it a configuration option. I mean,
yeah, maybe different devices.
Yeah, the benefit is that, yeah, I don't know. I think there's a lot of things to talk about. Like if the target's configuration changes, something external changes it, you can, then ONOS config is really the source of truth, and it's enforcing what it has, like what it thinks the target should be. And so if somebody goes and changes something, ONOS config will say no.
Yeah, that's what we do with the flows, right? For example, through open flow, when we periodically poll the flows, we said, oh, this is not supposed to be here, or you're missing one, and we reapply it. But there's definitely penalty, and to the overhead, right?
Yeah, that's why I'm unsure.
But
I don't know if it's a good idea or not.
Strategies could be applied, right? For example, detecting a device restart or something like that, then we could force basically a fetch of the configuration
Right, or a full resynchronization.
But then, that comes with the drawback of not being able to catch external updates that happened since then, right? So different drawbacks.
Yeah, I mean, is there any, I suppose it's kind of out of band of GNMI is like having, some kind of change ID on the device side, to say like this, this was the last configuration change I got, and if that's not the same as what ONOS config thinks it is, you trigger a full resynchronization or something like that. But not every device would have that, and it's kind of out of band of GNMI. So then, your alternative is read the whole config back from the device and do a delta, because like it mightn't just correspond to exactly the kind of changes you have. So like, you're keeping it as a full configuration anyway. You're effectively flattening down the transactions in the target.
But I like basically the flattening into the overall configuration that exists between on a boundary between the network change and the target change. I really like that because that sort of kind of resets things, and the complexity on either side is contained. And puts kind of a firewall.
And you always have the details of what the individual change was in the transaction anyway, so you can roll it back on the full configuration.
And it's one less possibility for inconsistency actually creeping into the system.
That was, I mean, you're right, it was a complete duplicate of the change that was in the network change was inside in the device changes.
And that log was really difficult to keep the two consistent because the network change log was already written, and so you had to make sure that things were appended to the device change log in the same order.
Well, and scalability will be improved too, right? In the sense we're dealing with much, we're reducing, in some cases, we're halving the number of entities that need to be tracked.
The other benefit is from the northbound. Would this be true? Like from the northbound, we'll say, when you were doing a GNMI get, what we were doing is we were layering together all of the individual device changes dynamically on the fly, and basically now you've calculated them all in the configuration.
It's already there.
You don't have to calculate it again. That would give a performance benefit too. Okay.
All right. Adib, do you want to do this part?
Okay. So there are a few other controllers that we would like to add. So one of the main reasons is that so far we were using a shim layer on top of the topology object as a device, but we want to migrate from this pattern to use the entity kind relationship pattern that we are using in, for example, in ONOS E2T. So technically, we need to create some entities and relationship between those entities. For example, we need a controller to create ONOS config entities, which is technically the source of the control relationship between a ONOS config pod and the target. So we need a new controller to create ONOS config entities in Topo and listen to the ONOS config entity changes and then react to those changes. For example, in ONOS E2T, we have a release mechanisms on ONOS E2T pods. Whenever there is a crash in one of those pods, the old entities, there is a lease on each of those entities, and if it gets expired, for example, if the node never gets restarted, the old entities will be cleaned up with the controller. So that's the responsibility of this controller to create the ONOS config entity. And the next slide, please. So we also need a connection controller. This controller is responsible to listen to the target entities, ONOS config entities, and control relationship, and also the southbound connection changes. And based on those changes, make sure that the connection is open. So create a connection to the target. Whenever, for example, we create a target entity, outside of the ONOS config. And then to make sure that we create a connection to the target, and that connection will be kept open as far as the target is there. Also, we want to create a control relationship between the ONOS config entity, which is created by the node controller, and also and the target to represent each connection. Technically, the control relationship represents the connections between the target and ONOS config entity. So these are the missing pieces that we don't have right now. So technically, we don't model the connection as the control relationship. We don't create ONOS config entities. So the only thing right now we create is just the device object, and we use that device object to make a connection to it. But we need to migrate from this pattern to this new pattern. So most of these patterns and these controllers already implemented in ONOS E2T. We have a pretty good idea how to implement these things. So it's just a matter of copying some of the packages from the E2T and change it a little bit to make it work for the ONOS config. So I don't know if the mastership controller is also needed or not. So this is something that we need to decide. If it's not needed, we can completely remove it. But we also already have a code for this one based on this new pattern. So to assign the mastership to each of the connection and control relations.
Yeah. So the connection controller really is needed so we can figure out when a device disconnected, which means it potentially could have restarted, and we need. I mean, that's one of the big things that we need to fix.
So this connection controller is basically connecting an ONOS config instance to a device.
Mm-hmm. Yeah.
How is that different from mastership?
Well, they actually work in tandem. So so basically, the connection controller is basically making sure that topo reflects so actually all these controllers work together. So the node controller makes sure there's a representation of the ONOS config node in topo. Somebody else put the target in topo, and then the connection controller is making sure that there's is basically creating relations. It's trying to connect to a target and then creating relations. And so we can use that. We can then use topology to tell if a connection went down. Like if a connection is lost, the connection controller will get rid of the relation, and then and then say the configuration controller can react to that and say, oh, the target might have restarted because it disconnected and reconnected, so we need to resync. And then mastership, if we do need mastership, mastership is basically the mastership controller will elect a master for each independent relation. So I'm trying to remember. Yeah, so that if there are multiple connections between ONOS config and ONOS config pod and the target, then because ONOS config will also be continuously trying to connect to things, and we've seen cases in E2T where even though a connection appears to be down, like the device is still sending information and things like that. And so if we do,
so that's for the case in which a target is created and two ONOS config instances creates a connection with the target,
or even one, yeah, or even one instance.
If it's one, then the mastership controller job, it's easy because there is one connection, is the only one that can talk to that guy, so it's master.
We have the corner case of the terminating pod, right? And it's restarting.
Yeah,
pod.
it's weird. There are weird things that I'm hoping that we don't need it, but
My suggestion would be to try to avoid it, because we should probably just go, given the relatively low throughput of operations that we have to deal with relative to like E2T or other type of controllers, I would suggest we go with a restart strategy. So meaning we just normally would run with a single pod and to avoid all of that stuff. But we should definitely design it so that we can have redundancy, just even like for upgrade capabilities. Like it would be not a norm, but kind of a transient situation where you might have multiple pods competing for mastership.
Yep.
Yeah, as Jonathan said before, it seems like that being configuration based, even if you have two different pods pushing the same configuration to the device, it won't be a problem.
Yeah, with a new level trigger approach, yeah.
Because the first one pushed the configuration, the second one will fetch it and say, oh, it's already done. Good.
Yeah. Now, one thing, a quick question on this on tracking the connectivity via relations. Now, this is something that we didn't have. We didn't have relations when we originally designed ONOS config. So we shoved the information about the protocol connectivity into the protocols aspect. We no longer really need that, do we?
Sure, yeah.
We should probably just roll it up. So that we just basically capture all of that relationship, all of that through the relation. And if you need to attach some information, it would be attached to the relation, not to the target.
And say if ONOS config was to go away or restart, like from the topo side, is there some controller cleanup there?
Yeah, so this is stuff that we already, a lot of this code is from E2T, and this is all stuff that we solved in E2T, but yeah. Basically the way that the node controller, every node that's, so node A is responsible for creating its own entity, and any other node are responsible for trying to get rid of its entity. And so they, so if you delete a pod and a new pod comes back, the new pod will say, well, it'll find the other entities and delete them, and that will cause the relations to be deleted.
Yeah, the only time you'll be left with some dangling stuff is when all of the instances of that node disappear. But that's usually represents some sort of a pretty significant boundary condition, the deformed state.
The good thing is that the solutions that we have right now work for single node or multi-node. So the algorithm is the same. So it doesn't matter how many ONOS config nodes you run. So even for mastership, I don't think it's gonna add a huge complexity to ONOS config, because it doesn't really matter if you run it as a single node or multi-node. So because anyway, you are running things in a cluster. So when you solve the problem for single node and the algorithm works for that, it also works for multi.
Yeah, I mean, that's clearly the best, yeah. Because then makes it upgradable. We can, if we do decide to scale it, we can.
Yeah, it is good for upgrades. Yeah. Times it anyways. Oh, right on time.
Cool. So this was great overview. So is there any other questions on this, or?
So far everything seems clear. The moment I start trying to do something, I realized that I didn't understand anything. But it's a different topic.
Yeah, so on Friday then we'll be more talking about it from the dimension of the configuration itself, right? In terms of the leaves and paths and the plugins and things like that, right? Is that correct?
Yeah, and Yang and all of those.
Yeah, and then so we can also cover probably we will cover mostly the direction in which we're heading with the plugins rather than where we came from, because that'll be more. Because the other stuff is a little bit convoluted, so we wouldn't want to. We're
probably going to talk about it Friday, but the part that I haven't quite figured out yet is how the plugin are somehow connected to the configuration, because I imagine like each configuration matches to a particular device type that is defined in the plugin.
Exactly.
Like that entire part is a little fuzzy to me, but I guess that's the topic you're covering Friday.
Yeah, I mean, what was kind of in there in Jordan's presentation today is that the internal representation, how things are stored internally, is something that basically is, you didn't get into detail, but that's some detail we'll get into. So, you know, the GNMI comes in, we change it to an internal representation that's attached to a network change and a device change in the current thing. They will stay the same, I presume, like in the transaction. And we'll cover that on Friday. And actually, I want to talk on Friday a bit about the future direction too. And, you know, we're talking about guardrails, which are a way of implementing business rules, you know, sort of leaf rules and how we might achieve that. It's not fully complete yet either, you know. And then the other thing is, like, every model type is an island in ONOS config, you know. So say, for instance, you'd either 3.0 and you'd either 4.0, and basically the configuration of two could never make any reference at all to each other, you know. So so basically we might want to be able to make a reference across to something of a different model, you know, and how we might approach this from either as well. So we'll cover all that. Okay, yeah, I feel a bit inadequate after your slides, Jordan. I better brush up my slides.
All right, so I think we can close the recording. Sounds good.